Okay, folks, now we're going to do section 2.4, which has to do with matrix inverses. And we're primarily going to do this using Octave Online. We're not going to do too much hand calculation here. Let me just remind you of something which we did talk about before. So here's Octave Online. There's a special matrix for each dimension called the identity matrix. So let me just put a comment. See, if I remember in Octave Online, if you just put a percent sign, you can write anything you want. It's just a comment. So these are inverse matrix. Okay, the inverse matrix. And one, let me make this a little smaller so you can see it. Okay, sorry about that. So inverse matrix is this. So and in Octave, it's this kind of crazy thing. You do I3, let's just say. So that becomes an identity matrix. I'm sorry, I said inverse matrix. I even misspoke. This is called the identity matrix. And in Octave Online, you use the word I, which is kind of silly. So I5. So this is a 5 by 5 matrix. It is 1 on the diagonal, and it is 0 elsewhere. So that is a special matrix. That's called the identity matrix. Now, here's a problem. Suppose I have any old matrix. Can I find another matrix so that I multiply it times the original matrix and I get the identity matrix? Is there such a thing? And the answer is, yeah, sometimes. Sometimes there is, sometimes there isn't. Okay. But if you go back to real numbers, forget matrices for the moment. You go back to real numbers. If I have the number 5, what can I multiply 5 by times something to get 1? And the answer is 1/5. What can I multiply -2 by to get the answer 1? -1/2. So it looks like for any real number, I can find another number to multiply it and get the answer 1. Is that true? It is true, except it's not true for 0. I can never find something to multiply 0 by to get 1, because as soon as I multiply by 0, you just get 0. Now, matrices are a little bit more complicated. 1 is like the identity matrix. So when you multiply two matrices together, you get another matrix. Can I find a matrix so if I multiply the first matrix times the second matrix, I get the identity matrix? And that's what we're going to study in this section. Because the answer is a little bit complicated. Sometimes you can, sometimes you can't. All right, so the idea is called the inverse matrix. So B is an inverse matrix of A. If A times B is identity. Turns out, if A times B is the identity, then B times A is also going to be, well, no, not necessarily. But for matrix, if this is both true, then B is called the inverse matrix of A. Okay, now how do you know if two matrices are inverses? Well, what you do, the simplest thing to do is just multiply them together till you get the identity matrix. So here's A, here's B. If you multiply A times B, notice it's going to be a 2 by 2 matrix, and there it is, the identity matrix of size 2. If you multiply B times A, you get the same thing. So B and A are inverses. By the way, if A is an inverse of B, then B is an inverse of A. Now, here's an example, and I'm not going to go through all the explanation, but it turns out that you can have matrices that look perfectly reasonable, but they just don't have any inverse. So the inverse of this matrix does not exist. And they go through a big story about why that's true, and I'm not going to go through their story, but just so you know, some things can happen, some things can't happen. Okay, folks, sorry for the interruption. So we talked about an inverse matrix. There's a little theorem here, which we're not going to go through, but it just says basically if A has an inverse that's called B, and A has an inverse called C, then B has to be equal to C. In other words, the inverse is a unique inverse if it exists. It may not exist, but if it does, then it's unique. Okay, so that's an important concept. Now, here's another sort of interesting, cute exercise. We're going to use this a little bit in some of the homework, but it's just a fact that if A is some matrix, I don't really care what it is, if it's true that some power of A, that means A times A times A, is equal to the identity, then you can easily find the inverse, because the inverse is the one less power. So if A cubed is the identity, A cubed would be A squared times A. That's just algebra. So A squared then would be the inverse, because here's a matrix times A, and you get the identity. So that must be the inverse. You could also do it the other way. A times A squared, so therefore A squared is the inverse of A. Okay? So that's a nice property. If you have a matrix that has some power, it doesn't have to be cubed, it could be any power. There's some power of the matrix is the identity, then you can always find an inverse. So that's a nice thing to happen. Something else which we don't use too much here, but it's called the determinant. And there's this thing called the adjugate. Don't worry about that. We're not going to use that. But the determinant of a matrix is a number, and we will definitely be doing determinants later on. So they're giving you a little introduction here to determinants. We'll skip over that because we don't need it right now. And there's a little, if you have a 2 by 2 matrix, there's an easy way to find the inverse. We don't need that right now. Inverses in linear systems, nice theory. Now, here's actually something important. If I have and we did this before actually, but we didn't call it inverse. If I have a system of equations, and the left side is 2 equations and 2 unknowns, or 3 equations and 3 unknowns, in other words, the square thing, and the right side is a vector, then I can find the solution to this by letting A be the coefficient matrix. Notice that A is this, 5, negative 3, see, 5, negative 3, 7, 4, so that's a matrix, square matrix. And the B over here is something, it's a column vector. Then the inverse of A, and I'm going to show you on Octave online how to find the inverse. It's real quick. You just find the inverse. Okay? So the inverse of A is some matrix, which they tell you what it is here. We'll do it on Octave. And so the solution to this system of equations is X is equal to A inverse times B. It's just like if you had a linear equation in algebra. If I have 3x equals 7, then x equals 7 divided by 3. Or x equals 1/3 of 7. In other words, whatever was multiplying x, you divide by that, or you find the inverse of that, and then you get your answer. Okay? Now, how do you do in matrix inverses? That's kind of a pain if you're doing it by hand. We're not even going to study it by hand. There's a way to do it by hand, and it has to do with reducing the matrices and blah, 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 blah. We're not going to do that. We're going to just do it by the Octave online. Okay. There's a connection between transposes and inverses. If A has an inverse, then A transpose also has an inverse. And you can figure it out by this formula. I think I'm not going to go through that right now. But there's just so you know, there's a connection. Oh, here's the one thing I wanted to mention before. Remember in the previous section, I said never change the order of multiplication of matrices because you're going to get a different answer if you change the order. But here is one situation where it looks like you're changing the order. So if A and B have inverses, and you multiply A times B, so you get some other matrix, and you ask, does that matrix have an inverse? And the answer is yes. If A and B have inverses, then A times B also has an inverse, and it's equal to B inverse times A inverse. So here's one scenario where when you take the inverse, just like when you take the transpose, when you take the inverse of the product, it's the product of the inverses in the reverse order. So that's an important thing to know. Proof. Blah, blah, blah. I'm not going to do that because it's a proof. Square matrix is invertible if and only if the transpose is invertible. Okay, fine. And we're not going to go through this theorem. There's a connection between being invertible and the rank. I don't think we need to know this right now. Maybe we'll come into that later. We'll talk when we talk about inverse transforms, but not in this section. Oh, here we go. Inverse transform. Okay, but we're not going to really go into too much theory on this. So this says if you have a transform by a matrix, then is it invertible? You may remember from algebra if you have a function and you ask for what's the inverse function, there was kind of a procedure for finding the inverse function, and the answer was also, well, there's not always an inverse function. Sometimes you can't find an inverse function. So I'm not going to go into all that right now. Exercises, just what you wanted. Okay, so let's look at some of the exercises. I put this over here. Okay, so here's your homework for section 2.4. And almost, not every problem, but almost every problem, you just throw it into Octave Online and get your answer. So let's do a couple of them together. Here, let's do problem 1. Show that these are, let's see, how am I going to do this? Let's move this over. Why do you not want to move for me? Because I'm not doing it the right way. Here's my Octave Online. Show that the matrices are inverses of each other. Now, I'm going to do it two ways, just to show you can do it this way. So I'm going to say let matrix A be the matrix 3, 5, semicolon 1, 2, semicolon B equals the matrix 2, negative 5, semicolon, negative 1, comma 3, semicolon, what is A times B? Now remember how this works. In Octave Online, the way you put matrices in, you put them in row by row, put them a semicolon between them. If you want to do multiple things on the same line, you put a semicolon and then you start doing the next thing you want to do. And then finally, here's what I really want to see. What is A times B? Aha! It's the identity matrix. What is B times A, by the way? It's the identity matrix. So if A times B is the identity, B times A is the identity. You can do it the same way again. Now, let me show you one little trick. I don't even have to name these guys. I could just say, let me do the same problem again, but now I'm not even going to give them any names. Here's a matrix. Doesn't have any name. It's just a matrix. Times, and here's another matrix. Doesn't have any name. But anyway, it's a matrix. And I can verify that that's the answer. Okay, so that's just a little Octave trick. You don't have to name everything. Okay, that's problem 1. Problem 2. Find the inverse. Okay, so here's a matrix. I'm going to find the inverse. So let me name the matrix. Oops, where is it? Here we go. So let's say A is the matrix. So I'll say A equals, we'll do the first one, 1 space, -1, semicolon, -1 space 3. There it is. What is A exponent -1? That's the inverse, is exponent -1. And there it is. And Octave, as you know, expresses everything in decimals. So the inverse of A is 1.5, 0.5, 0.5, 0.5. And if I want to verify that, what I could have done is say B equals that, and then say, well, what's A times B? 0. Notice, this is interesting. Notice that Octave made a 0 there because it is precisely a 0. In this case, it said 0 point blah, blah, blah. This is still 0, but what happens is internally Octave is making some internal calculations, and it may or not be exactly 0. I see I'm really going over on my tape here. So I'm going to stop here and then